Welcome back to the Deep Dive, where we dissect complex research and extract the most important insights to keep you at the forefront of AI. Today, we're embarking on a fascinating exploration into a groundbreaking new paper that's truly pushing the boundaries of large language models. We've been immersed in a significant new publication from Zipu AI and Tsinghua University. It introduces the GLM-4.5 series, and they're calling it the Agentic Reasoning and Coding, or ARC, Foundation Models. Our mission for this deep dive is to unpack the architectural innovations that underpin this new series, really dig into their multi-stage training processes, which are remarkably intricate, and then dissect the impressive performance benchmarks that firmly position GLM 4.5 as a very significant contender in the rapidly evolving open source LLM landscape. We're going beyond just the results, right? We want to understand how they achieved them and what the implications are for the field.
Indeed. This paper offers a remarkably in-depth look at how these researchers have engineered a single model designed to unify critical capabilities across these agentic reasoning and coding tasks. What's particularly fascinating here from an engineering perspective is their sophisticated approach to achieving both efficiency and multimodal training at scale, which we'll be exploring in considerable detail. Our focus will be squarely on the technical specifics and the empirical results, aiming to provide you, our listener, with a thorough, actionable understanding of this new model and its potential impact.
Okay, let's unpack this then. The core of today's deep dive is, of course, GLM 4.5. Before we get into the nitty-gritty, what exactly is it, and what's its grand ambition in the ever-expanding world of large language models? What problem are they trying to solve here?
Right. At its heart, GLM 4.5 is introduced as an open-source mixer of experts, or MoE, large language model. This architecture, it's increasingly recognized for its efficiencies. Specifically, its design features a substantial 355 billion total parameters, which sounds massive, right? But the real engineering marvel is that for any given task, a much more computationally efficient subset of just 32 billion parameters is activated. This means it leverages a vast knowledge base without incurring the full computational cost of dense models of similar scale. And furthermore, this architecture supports a sophisticated hybrid reasoning method. It allows for both a deliberative thinking mode for tackling complex multi-step problems and a direct response mode for immediate, straightforward answers. This dual capability is a critical step towards more nuanced and context-aware interactions. It enables the model to intelligently decide when to engage in complex thought processes and when to provide a swift, direct answer. Much like a human adapting their approach to a problem.
So it's not just big in terms of raw parameters. It's remarkably smart about how it's big, strategically activating only what's needed. And it can intelligently adapt its thought process based on the problem. That adaptive capability is genuinely intriguing. So with this intelligent architecture, what's the overarching goal for GLM 4.5? Are they targeting a specific niche or something much broader?
Well, the paper explicitly positions GLM 4.5 as a significant stride towards artificial general intelligence, or AGI. Their ambition is to move beyond mere task-specific excellence, where models are fantastic at one particular thing, toward unified mastery. Mastery of complex problem-solving, generalization, and even a degree of self-improvement. They specifically target three critical interconnected capabilities, which they've concisely termed ARC. First, agentic abilities, crucial for interacting with external tools in the real world, essentially acting as an intelligent agent. Second, complex reasoning, essential for tackling multi-step problems in highly structured domains like advanced mathematics and scientific discovery. And third, advanced coding skills, vital for real-world software engineering tasks, going beyond just simple snippet generation. The ambition here is profound, to provide a single, powerful, and importantly, open-source model that excels across all three of these domains. This has historically remained quite elusive in the open-source landscape, right? Many models specialize, but few unify these high-level capabilities. They emphasize that while proprietary models have shown strong performance in individual ARC domains, a truly unified open-source champion, capable of matching those specialized performances across the board, has been sort of a missing piece.
That's a bold ambition indeed. An open source model aiming for AGI by unifying agentic reasoning and coding. So the crucial question for our listeners, how does it stack up against the competition right out of the gate? Give us the headline performance figures, but maybe more importantly, give us the context that makes those numbers truly meaningful.
Okay. After multi-stage training on an immense 23 trillion tokens, a truly staggering amount of data and comprehensive post-training, GLM 4.5 achieves strong and in many cases leading performance across these agentic reasoning and coding, or ARC, tasks. Let's break down the key scores and their implications. For agentic capabilities, it scored 70.1% on TAU bench and 77.8% on BFCL-v3, which immediately puts it on par with a top-tier proprietary model like Claude Sonnet 4. But what's particularly noteworthy, especially for those interested in real-world agentic behavior, is its performance on browse comp. It achieved 26.4%. This isn't just a number. It means GLM 4.5 clearly outperformed Claude Opus 4, which scored 18.8% on this complex web browsing benchmark. It even edged closer to the O4 mini-high model at 28.3%. That's a massive leap for an open-source model in a domain requiring deep contextual understanding and multi-step interaction. Then in reasoning, GLM 4.5 demonstrated outstanding performance, scoring an impressive 91.0% on AME24, which is a highly challenging mathematics competition benchmark, also 79.1% on GPQA, a demanding scientific reasoning dataset.
72.9% on Live Code Bench, specifically targeting problems from a recent period, 2407-2501. And a notable 14.4% on Humanities Last Exam, HLE, which is designed to be incredibly difficult and really pushes the boundaries of current AI. These aren't just high scores, they signify a model capable of genuinely complex, multi-step logical deduction across diverse, challenging domains. Finally, for coding tasks, fundamental for practical AI applications. GLM 4.5 secured 64.2% on SWE bench verified and 37.5% on terminal bench. These results are particularly impactful because it means GLM 4.5 outperformed GPT 4.1 and Gemini 2.5 Pro on SWE bench and was remarkably competitive with Claude Sonnet 4. For SWE bench verified, it indicates the model can reliably fix a significant portion of real-world software bugs. These figures, especially when we consider its impressive parameter efficiency, aren't just benchmarks, they represent a significant step forward for the utility and capability of open-source models in practical software development.
That's truly remarkable, particularly, as you said, considering its parameter efficiency. It's one thing to achieve high scores with a colossal model, but to do so while being computationally lean is a significant engineering feat. But what about a more compact version? For our listeners working with different resource constraints or those who might not need the absolute full-scale model, is there a more accessible variant?
Absolutely. The researchers also recognize the importance of accessibility and practicality, which is why they concurrently release GLM 4.5 Air. This is a smaller, yet still incredibly powerful MoE model featuring 106 billion total parameters. This compact version represents a significant leap among models at the 100 billion parameter scale. It matches or even exceeds the performance of larger open-source competitors like Qwen 3 235B A22B and Minimax M1. This demonstrates that the architectural and training innovations they've developed can scale down effectively, maintaining strong capabilities even in a more resource-friendly footprint. For practitioners and developers, this means a high-performance model is available for a wider range of applications and hardware environments.
That commitment to scalable performance is excellent news for the broader AI community. And for those of our listeners who are eager to dig into the models themselves, perhaps run their own benchmarks or integrate them into their projects, where can they find these models and the associated tools? Is there a commitment to true open sourcing here?
Yes, there's a strong commitment to open sourcing, which is a significant contribution in itself. Both the full-scale GLM 4.5 and the compact GLM 4.5 Air are readily available. You can find them on z.ai, bigmodel.cn, and crucially, as open-source models on Hugging Face under the Xi.org organization. This level of accessibility means researchers and developers worldwide can inspect, utilize, and build upon these models. Furthermore, to ensure benchmark reproducibility and to genuinely encourage further research and community contributions, they have also open-sourced their evaluation toolkit, GLM Simple Evils, which is available on GitHub at github.com/xi-or GLM-Simple Evils. This transparency is vital for advancing the entire field.
Okay, let's transition now from the impressive results to the underlying engineering. We're talking about the architecture that makes these models tick. The paper heavily emphasizes the mixture of experts, or MoE, design. What's the core benefit they're aiming for here, and how have they implemented it in a way that differentiates GLM 4.5?
Right. The adoption of the MoE architecture in the GLM 4.5 series primarily aims to significantly improve computational efficiency, both for the training phase and, critically, the inference phase. For large models, this isn't just an optimization, it's often an enabling factor for deployment. They've implemented it using specific refined techniques. For instance, they employ loss-free balance routing, which is a sophisticated mechanism designed to prevent individual experts within the MoE from becoming underutilized or, lazy. Essentially, it ensures that the workload is distributed effectively among all specialized brains in the model. Additionally, they use sigmoid gates for the MoE layers. These act like intelligent traffic controllers, precisely directing the input to the most relevant subset of experts without overwhelming any single one. This careful implementation ensures that the core benefits of MoE selectively activating a smaller subset of parameters for a given input are fully realized, leading to efficient resource utilization.
Interesting. So it's about making sure all parts of the model's brain are working effectively without wasting computation. And they mentioned a particular design philosophy regarding depth versus width, which sounds a bit counterintuitive compared to what some other large models have prioritized. Could you elaborate on that choice?
Yeah, this brings us to a fascinating architectural choice that challenges some prevailing trends. Unlike some prior state-of-the-art models, such as DeepSeek V3 and Qinkai, which focused on increasing the width, meaning a larger hidden dimension and more routed experts per layer. The GLM-4.5 team intentionally reduced the width while concurrently increasing the height, or the number of layers. Their empirical finding from extensive experimentation was quite insightful. Deeper models consistently exhibited better reasoning capacity. This suggests that for complex, multi-step reasoning tasks, providing more sequential processing layers, even with a narrower computational path within each layer, is more beneficial than having wider, more parallel processing. It's almost as if deeper models allow for a more hierarchical, step-by-step approach to reasoning, which seems to pay dividends for logical deduction. This is a key insight for future LLM design, especially when prioritizing complex reasoning abilities.
So it's about the depth of thought, not just sheer brain size at each step. That's a truly counterintuitive breakthrough for how we design these massive models. Following that, what other specific components contribute to this enhanced reasoning capability, particularly within the self-attention mechanism, which is so fundamental to transformer architectures?
Well, within the self-attention component, which dictates how the model weighs different parts of its input, they utilize grouped query attention with partial row P. These techniques are well regarded for improving efficiency and for effectively handling long contexts. But what's particularly noteworthy is their decision to significantly increase the number of attention heads. They use 96 heads for a 5,120 hidden dimension. To give context, this is approximately 2.5 times more than a typical setup for a model of this hidden dimension. Counterintuitively, while this increased headcount did not improve the standard training loss, like perplexity, compared to models with fewer heads, it consistently and significantly enhanced performance on critical reasoning benchmarks like MMLU and BBH. This implies that these additional attention heads are contributing to a richer representational capacity that directly benefits complex reasoning, even if it doesn't manifest as a lower perplexity during pre-training. It suggests a decoupling between general language modeling performance and specialized reasoning ability. Additionally, they incorporated QK norm to stabilize the range of attention logits, which is a crucial detail for preventing gradient issues and ensuring training stability in such deep models.
That's a fascinating detail. A design choice that doesn't improve the traditional training loss, but demonstrably boosts reasoning performance. It really highlights the often nonlinear and sometimes surprising relationship between training metrics and a model's actual downstream task performance. Beyond training, what about inference efficiency, especially with MoE models, where rapid output is key for user experience?
Inference efficiency is paramount for practical deployment, absolutely. For both GLM-4.5 and GLM-4.5 Air, they implemented a clever optimization, adding a MoE layer specifically as the multi-token prediction, or MTP layer. This MTP layer is designed to support speculative decoding during inference. In essence, it predicts multiple future tokens in parallel, allowing the model to generate text much faster by essentially guessing and pre-calculating parts of the output. If these predictions are correct, it dramatically speeds up generation. If not, it falls back gracefully to regular decoding. This is a very effective way to further enhance efficiency during the inference phase, which is critical for real-world application, especially for agentic models requiring rapid iteration. And if we connect this to the bigger picture, the impact of these architectural choices, particularly the MoE design and the MTP layer, is clearly visible in their efficiency metrics. You can see from Table 1 in their paper that GLM 4.5 is exceptionally parameter efficient. It has only 355 billion total parameters, with just 32 billion activated at any given time. This is considerably less compared to models like DeepSeek V3, which has 671 billion total and 37 billion activated, or Qinkai, with a colossal 143 billion total but also 32 billion activated. This efficiency allows GLM 4.5 to achieve strong performance with significantly fewer overall parameters, effectively positioning it on the Pareto frontier for SWE bench-verified scores versus model parameters, as clearly depicted in Figure 2. This means they're getting more performance per parameter, which is a significant engineering feat, directly impacting the feasibility and cost of deploying such advanced models.
That's a compelling argument for their design philosophy. Building such a high-performing and efficient model, especially one aiming for unified ARC capabilities, requires not just clever architecture, but a robust training strategy. Let's delve into their pre-training and mid-training stages, starting with the foundation, the data. What kind of corpus did they use, and perhaps more importantly, how did they meticulously process it?
The pre-training corpus is indeed incredibly diverse. Billions of documents from web pages, social media, books, papers, and vast code repositories. But the sheer volume wasn't enough. They meticulously designed bespoke data processing pipelines for each source to ensure quality and relevance. For web data processing, the majority of English and Chinese documents, they implemented a sophisticated multi-stage quality scoring system. They intelligently divided crawled pages into buckets based on quality scores and strategically upsampled from higher quality buckets. This ensured that over 3.2 epochs of the highest quality data were utilized. This isn't just about repetition, it emphasizes high-frequency knowledge while also improving long-tail coverage. They also applied SIMDDUP, a semantic deduplication pipeline, which is more advanced than traditional minhash. SIMDDUP specifically targets and removes template-generated similar web pages that minhash often misses, ensuring genuine diversity. To support a broader linguistic base, they included multilingual data from crawled web pages and datasets like FindWeb2. Here, they leveraged a specialized quality classifier to judge educational utility, upsampling high-quality multilingual content. For code data curation, source code from GitHub and other platforms underwent rule-based filtering, then classification using language-specific quality models into 3 tiers. High-quality code was significantly upsampled, low-quality excluded. They applied the fill-in-the-middle objective, effective for understanding code structure. For code-related web documents, they used a 2-stage retrieval process, identifying code tags or using fast text, followed by quality assessment. Then a fine-grained parser reparsed selected pages to better preserve code formats, crucial for retaining semantic integrity. Lastly, for math and science data, from web pages, books, and papers, they used an LLM to score documents based on educational content ratio. A smaller classifier predicted these scores, and documents above a threshold were heavily upsampled. This holistic, multi-layered approach to data curation is truly foundational.
That's an incredibly sophisticated data curation pipeline, far beyond simple collection and filtering. It sounds like immense effort went into crafting the learning signal. How did they structure the actual pre-training process with this meticulously prepared data? Was it a single stage, or were there distinct phases?
The pre-training was indeed split into 2 distinct stages, reflecting a carefully considered curriculum. The first stage primarily focused on general documents from web pages. This phase aimed to establish a broad understanding of language, facts, and general world models, the foundation. In the second stage, they specifically upsampled source code from GitHub and web pages related to coding, mathematics, and science. This targeted upsampling later allowed the model to refine its understanding and capabilities in these critical domains, building upon the generalized knowledge from stage 1. This sequential, domain-focused approach helps the model specialize without sacrificing general comprehension.
And then comes what they call mid-training. This isn't a typical step in many LLM pipelines. It sits between pre-training and post-training. What's the precise purpose of this intermediate phase? How does it differ from traditional pre-training or even fine-tuning? It sounds like a specialized boot camp.
Mid-training is indeed a crucial and distinct intermediate phase, designed to further boost performance in important application areas. It bridges the gap between broad pre-training and highly specialized post-training. It goes beyond general document exposure by using medium-sized, domain-specific datasets, crucially including instruction data. This instruction data is key, providing explicit guidance on how to perform tasks, vital for agentic and reasoning capabilities. This phase had 3 key components. First, repo-level code training. The focus here was understanding and generating code within entire software repositories. They did this by concatenating multiple code files from the same repo, letting the model learn cross-file dependencies. To enhance real-world capability, they included model-filtered issues, PRs, and commits from GitHub, concatenating related items and organizing commits in a diff-like format. Importantly, the sequence length was significantly extended from 4K to 32K tokens here to accommodate these larger contexts. The second component was synthetic reasoning data training. For advanced math, science, and coding competitions, they generated highly structured synthetic reasoning content, collecting questions and answers, then synthesizing detailed step-by-step reasoning processes using a specialized reasoning model. This provides structured, high-quality, scalable reasoning examples. The third component was long context and agent training. To enhance the ability to process very long inputs, the sequence length was extended again, from 32K to an impressive 128K tokens. achieved by upsampling long documents from the pre-training corpus. Additionally, large-scale synthetic agent trajectories were incorporated here, simulating interactions with tools and environments, laying crucial groundwork for agentic abilities. This mid-training phase is really about targeted skill acquisition before the final refinement.
So it's about gradually extending the model's working memory and teaching it domain-specific problem solving. What does this mean for the maximum sequence length progression? It sounds like they pushed the boundaries significantly, but how did they manage that without truncating critical information?
You're right, the progression is quite aggressive and strategically managed, as shown in Figure 3 of their paper. Started at 4,096 tokens in pre-training, then extended during mid-training, first to 32,768 tokens for tasks like repo-level code, and eventually to an impressive 131,072 tokens for long context and agentic training. This sequential increase allowed gradual adaptation to longer dependencies. They specifically note that while random truncation was used for data augmentation in pre-training, which can help generalization, best fit packing was applied exclusively in mid-training datasets. This was a crucial choice to avoid truncating vital reasoning processes or complete repo-level code structures. For these complex tasks, preserving the entire coherent sequence is essential for learning the full problem and solution.
That's a huge jump in context window, 4K to over 128K tokens. And the packing choice shows deep understanding. To manage such a massive model and data volume across these stages, what optimization strategies did they employ hyperparameter-wise? Any key lessons learned there?
The hyperparameter choices are indeed crucial to scale. They employed the muon optimizer for most parameters, excluding word embedding, bias, and RMS norm weights. For muon, they set Newton-Schultz iteration steps to 5, momentum to 0.95, and scaled muon's update RMS to 0.2. The key insight: they found muon significantly accelerated convergence and critically tolerated larger batch sizes, vital for efficient training at trillions of token scale. For the learning rate, they opted for a cosine decay schedule, warm up from 0 to 2.5 E4, then smoothly decaying to 2.5 E5. They explicitly highlight avoiding the traditional warm-up stable decay schedule due to observed underfitting in earlier experiments. This suggests a continuous smooth decay performed better, letting the model keep learning effectively. The batch size itself was gradually increased from 16 million to 64 million tokens during the initial training phase, then held constant. For regularization, a weight decay ratio of 0.1 and notably no dropout. The absence of dropout suggests confidence in the model's generalization without needing to randomly turn off neurons, testament to data and architecture quality.
For long context modeling, they adjusted ROPI's base frequency from 10,000 to 1 million Belin when extending sequence length to 32K, standard practice for expanding rotational position embeddings. Lastly, a subtle but critical detail for MOE models. They meticulously managed the bias update rate for loss-free balance rounding, setting it to 0.001 for the first 15 trillion tokens, then 0.0, and also applied an ancillary sequence-level balance loss. These specific measures are essential to prevent extreme imbalance, ensuring MOE experts are continuously utilized. The MTP loss weight was adjusted too. These detailed choices underscore the depth of their optimization efforts.
Okay, beyond pre and mid-training, the paper details a sophisticated post-training process. They call it expert model iteration. This sounds like another layer of specialization, taking the generalist model and really sharpening its core capabilities. What are the two main stages here, and how do they build on everything we've discussed?
Post-training is indeed divided into two distinct but interconnected stages, designed to meticulously refine and then integrate capabilities. First is Stage 1, expert training. Here, they construct specialized expert models, each honed for optimal performance in one of the three critical domains: reasoning, agentic behavior, and general chat. Each expert is rigorously optimized for its specific task type, becoming a specialist. The second stage is Stage 2, unified training. This is where the integration happens. This stage employs sophisticated self-distillation techniques to merge the distinct capabilities of these multiple specialized experts into a single, comprehensive generalist model. The goal is that this unified model becomes capable of truly hybrid reasoning, seamlessly switching between deliberative thinking and direct response modes based on the task's complexity. It's about creating a model that's both a collection of specialists and a versatile generalist.
Makes sense. Train the specialists, and then teach a generalist to embody all those specializations. Supervised fine-tuning, SFT, seems crucial in both post-training stages. How does it fit in? What function does it serve at each point?
SFT is indeed foundational, performed at the very beginning of both stages. In expert training, its primary role is to provide a cold start. Think of it as giving each specialist model its initial foundational knowledge: basic chat, initial reasoning, preliminary tool use understanding. This establishes a strong baseline before the more advanced RL phases begin. In the unified training stage, SFT's purpose shifts. Here, it's about distilling the distinct capabilities learned by the individual experts into the single generalist model. This distillation ensuring the unified model can handle various task types and intelligently balance reflective versus immediate responses. They achieve this critical balance by meticulously structuring the training data, combining examples demonstrating full reasoning processes with data lacking explicit thought processes, training the model to intelligently switch modes.
And they even optimized function calls, which is absolutely crucial for robust agentic behavior, by reducing character escaping. That sounds like a really practical, real-world improvement that often gets overlooked but can have a huge impact. Can you explain that innovation?
Yes, this highlights an important, often underestimated challenge: optimizing model interaction with external tools, especially with structured data like JSON or code. For function call parameters, often in JSON format containing code or complex strings, extensive character escaping is traditionally required. This forces the model to generate numerous backslashes, increasing its learning burden and often leading to errors. To mitigate this, they proposed a novel function call template. This template cleverly encapsulates keys and values within unique XML-like special token tags. This innovative approach drastically reduces the need for escaping, allowing most code or string data to be represented natively within the output without compromising performance. Figure 4 in their paper illustrates this well with a weather query example, showing a much cleaner representation. For developers building agents, this means more reliable, readable, and efficient tool interactions.
That's a truly elegant solution to a very practical problem. Beyond SFT and tweaks, what about ensuring the quality of training data and responses during post-training? A multi-stage rejection sampling pipeline sounds rigorous.
They indeed employed a comprehensive multi-stage rejection sampling pipeline for highest quality. This involves several crucial steps. First, systematically removing repetitive, short, or truncated samples, or those failing reasoning format checks. Second, for objective answers, like math or code rigorous correctness verification. Third, for subjective questions, using sophisticated reward models to filter responses, aligning with desired quality and preference criteria. Fourth, critical for agents, ensuring strict adherence to tool invocation protocols and verifying successful trajectory completion. This rigorous filtering is key to maintaining a high signal-to-noise ratio. Beyond just filtering, they also found intelligent prompt selection and response level scaling highly effective. Specifically, filtering prompts in the bottom 50% based on response lengths resulted in a notable 2–4% improvement in math and science tasks. This highlights the value of focusing compute on challenging high-signal prompts. Furthermore, generating 4 responses per prompt response scaling and selecting the best one brought an additional 1–2% gain. This implies that, for harder problems, giving the model chances for self-correction and selecting from diverse outputs enhances final performance.
It's impressive detail and quality control. But let's talk about generating agentic data. How did they automate creating agentic SFT data? That must be incredibly complex given the need for diverse environments, multi-step interactions, and realism. Manual annotation seems prohibitive.
Automating agentic SFT data construction was a cornerstone, involving 4 meticulously designed, scalable steps. First, agentic framework and tool collection. Gathering comprehensive frameworks, real-world tool APIs, setting up MCP servers for interactive environments. Crucially, they also leveraged LLMs themselves to automatically construct and simulate additional tools, dynamically expanding environment diversity. Powerful data bootstrapping. Second, task synthesis. Based on collected frameworks and tools, they automatically synthesized vast agentic tasks. For mature frameworks, LLMs generated relevant queries. For fragmented tools, LLMs constructed tasks around representative functionalities, including single and multi-step scenarios. Third, trajectory generation. For each synthesized task, existing capable LLMs generated full end-to-end tool call trajectories, thoughts, calls, observations. Using an LM as a user simulator, complex multi-step tasks were converted into multi-round dialogue trajectories, simulating real user interaction. Finally, quality filtering. Critical step. Multiple judge agents evaluated each trajectory for successful task completion. Only successful trajectories were retained, ensuring high-quality training data representing effective agentic behavior. This automated pipeline is key for scale.
Okay, now to the sophisticated heart of their post-training. Reinforcement learning, RL. This is where models often gain their final nuance. It sounds like they tailored their RL approach to each domain: reasoning, agentic, general chat, recognizing unique challenges. Let's start with reasoning RL. What's its distinct challenge and how do they approach it?
Reasoning RL focuses on domains needing logical deduction and verifiable accuracy math code generation science. The distinct challenge. Reward signals are often high precision, either right or wrong, leading to sparse rewards. Makes learning tricky. Their overall RL algorithm builds on the GRPO framework, but importantly, they exclude the KL loss term, suggesting a focus on direct reward maximization for these precise tasks. To address the evolving model proficiency, mismatching static data, a common RL pitfall, they used difficulty-based curriculum learning. They observed early on, overly difficult data gives all 0 rewards, no signal. Later, too simple data gives all 1 reward, no signal variance. So they implemented a 2-stage difficulty curriculum. As the model improved, they switched from moderate to extremely difficult problems, sourced strictly from a pool with verified correct answers. This ensured continued improvement and high signal quality. Visible in Figure 5 for Aang-24 is showing sustained gains where static curricula plateau. This brings another fascinating insight about sequence length in RL. How does it affect RL, especially given past research suggesting multi-stage RL with increasing lengths? Their experiments showed single-stage RL directly at 64K output length was more effective. Since SFT already conditioned the model for 64K responses, they found shorter RL stages could paradoxically cause it to unlearn long context capabilities, leading to irreversible performance drops, strikingly shown in Figure 6. A critical finding challenging conventional wisdom, emphasizing preserving learned long context abilities. To balance accuracy and exploration, they used dynamic sampling temperature. Fixed temperature is often suboptimal. When average rewards stabilized, indicating convergence, they intelligently increased temperature to encourage diversity. A sophisticated quality control mechanism prevented performance drops by periodically evaluating on a validation set across temperatures. The next phase's temperature was set to the max value, not causing more than a 1% drop, ensuring a robust balance. For code and science RL, often less studied in RL lit than math, they made specific innovations. For code RL, token-weighted mean loss proved critical for efficiency and faster convergence, providing a finer-grained stable gradient signal versus sequence mean loss. Figure 7 left. Also helped alleviate length bias and suppress simplistic samples. For science RL on GPQA Dion, using exclusively expert-verified multiple-choice questions led to significantly better performance than mixed-quality data. Figure 7, right?
Right.
Powerfully underscoring that even for simple formats, rigorously filtering the RL data pool for high-quality, challenging instances is paramount.
That's a deep dive into refining reasoning, addressing core RL challenges like sparse rewards and maintaining long context. How do they tackle agentic RL, where actions, environments, and more complex rewards are central? This domain feels inherently messier for RL.
Agentic RL is indeed different, building on these insights but adapting them for sequential decision-making in interactive environments. Focused on web search and code generation agents, leveraging their built-in verifiability for dense, reliable rewards. For data collection and synthesis on web search, they developed a sophisticated pipeline generating demanding multi-step question-answer pairs, requiring reasoning across multiple web sources. Combining automated multi-hop reasoning over knowledge graphs with human-in-the-loop extraction for robust RL training signals. For software engineering, they curated real-world GitHub PRs and issues for a realistic benchmark with user prompts and executable unit tests, evaluated in a hardened sandbox. For RL and iterative self-distillation, they adopted the group-wise policy optimization algorithm. For web search, the final answer accuracy was the reward. For coding agents, SWE data with verifiable test cases was the primary reward signal, a key innovation, a process format penalty. If the model failed the correct tool format, the trace got 0 reward, explicitly guiding towards correct tool interaction. Since Agent RL is time-consuming due to environment interactions, they employed iterative self-distillation, performing RL, using the RL model's responses to create a superior SFT model, then doing further RL, progressively increasing difficulty, bootstrapping performance efficiently. What's truly fascinating here, a crucial distinction for agents, is how they achieve gains through scaling test time compute via interaction turns. Unlike reasoning models scaling by generating more output tokens, thinking deeper, agent tasks leverage test time compute by continuously interacting with the environment, e.g., searching the web or writing internal test cases for self-correction and coding. Figure 8 clearly shows browse comp accuracy scales smoothly with browsing effort, interaction turns, demonstrating that more iterative engagement directly translates to higher performance, mirroring human problem-solving through feedback loops.
That distinction between scaling tokens versus interaction turns for agents is profound. It totally reframes how we think about computation. And finally, general RL, the culmination, bringing all specialized feedback together for a robust, well-rounded model. What's the goal here? How do they integrate diverse feedback for holistic improvement?
General RL is the capstone. aiming for holistic performance improvement across all capabilities, actively remediating residual issues, strengthening key strengths, uses a powerful multi-source feedback system, rule-based, human, RLHF, and model-based, RLAIF. This hybrid framework provides robust, comprehensive training signals, leveraging each source's advantages while mitigating limitations. For holistic RL, they built a balanced data set of 5,000 prompts across 7 primary, 33 secondary, 139 tertiary categories, ensuring broad coverage. Reward signals came from human preference annotations, evaluating instruction following, safety, factual correctness, and AI feedback, objective ground truth scoring rubrics. Merging sources yielded more reliable signals. Instruction following RL specifically targeted improving understanding of complex, nuanced instructions, developed a fine-grained taxonomy. 7 major, 151 minor constraint types. A dedicated training set of challenging instructions pushed boundaries. The feedback system combined deterministic verification rules, a reward model, and a critique model. This hybrid system mitigated reward hacking during GRPO training, enabling continuous, steady improvements. Figure 9. Function calling RL is split into 2 complementary approaches: stepwise, rule-based RL, and end-to-end multi-turn RL. Stepwise RL used a strict rule-based reward, 1 if format correct and the exact match, 0 otherwise, for explicit tool invocation procedures, enforcing precision. End-to-end multi-turn RL rewarded based on full task completion after complete trajectory, allowing optimization of action policy through trial and error with tool feedback, enhancing autonomous planning for complex multi-step tasks. This dual approach gives micro-level precision and macro-level tasks success optimization. As a final targeted stage, pathology RL rectifies specific issues: language mixing, excessive repetition, formatting mistakes. While penalizable in general RL, their low incidence 1% made it sample efficient. By curating a specific dataset of prompts triggering these behaviors, they could impose efficient penalties, lowering residual error rates for these issues, ensuring cleaner, reliable output.
All these complex RL stages, unique data, rewards, optimization goals, must require an incredibly robust infrastructure. What are the key elements of their Slime RL framework enabling this? Sounds like an engineering marvel.
The Slime RL infrastructure is indeed sophisticated, built for flexibility, efficiency, extensibility, crucial for diverse RL tasks. A core feature is its flexible hybrid training and data generation architecture. Supports both a collocated, synchronous mode, training inference on same worker, dynamic sampling, reduced GPU idle for general reasoning RL, prioritizing low latency, and a disaggregated asynchronous mode for protracted agentic tasks like software engineering. This decouples rollout from training, allowing agent environments to continuously generate data without stalling policy updates. RAY framework enables flexible engine placement. Unified HTTP endpoint interface and centralized data pool handle heterogeneous agent frameworks. Figure 10. Improves overall throughput. To address rollout efficiency bottleneck, they implemented accelerated rollout with mixed precision inference. Use BF16 for training, but FP8 for inference during rollout. Perform online, blockwise FP8 quantization of parameters before rollout. Dynamic on-the-fly quantization significantly improves data collection throughput, faster trajectory generation. Finally, their agent-oriented RL infra design includes several innovations. High concurrency Docker-based runtime for isolated environments, reducing rollout overhead. Fully asynchronous RL training loop handles long horizon rollouts and variable lengths, partitions GPUs into dedicated rollouts and training engines, preventing underutilization. Unified HTTP endpoint and centralized data pool cleanly decouple task-specific rollout from core RL training, enabling seamless integration of diverse agent frameworks, offering versatility.
That's a profoundly optimized system, clearly built with large-scale RL nuances in mind. Let's move to the exciting part, the results. How does GLM 4.5 perform across their extensive evaluation suite? From base model capabilities to general abilities and safety, what's the real-world significance?
They evaluated on several fronts, starting with the base model, revealing inherent capabilities before fine-tuning. The evaluation base models table 2 showed GLM 4.5 based the pre-training checkpoint. Not instruction-trained, exhibited remarkable stability and strong performance across English, code, math, Chinese benchmarks, e.g. 78.1% on Eval Plus code, 79.4% on GSMA-K, math 86.9% on C-Eval Chinese. Validates their concept of unifying abilities into one model, showing robust foundational knowledge even before specialized training. Then, a comprehensive evaluation on 12 key ARC benchmarks. For agentic abilities, Table 3, GLM 4.5 averaged 58.1%, ranking well. Notably outperformed Gemini 2.5 Pro on TAE Bench, On BFCL v3, achieved best overall score among baselines. On Browse Comp, its 26.4% was close to O4 Mini, significantly better than Claude Opus 4. Implies practical web interaction capability, competitive with leading proprietary models. For reasoning, Table 4 averaged 67.7% on AA Index, outperformed OpenAI O3 on AIM24, 90.0% CRSI code, 41.7% on Advanced at 41.0%, close to DeepSeek R1 0528 overall, strong general reasoning. For coding, Table 5 averaging 50.9%, exceptional performance. Outperformed GPT 4.1, 39.5%, and Gemini 2.5 Pro, 37.2% on SW Bench Verified, meaning it could fix more real-world bugs. On terminal pitch, 37.5% surpassed Claude Sonnet 4, 35.5%. Best competitor for Claude Sonnet 4 among evaluated models. In general abilities, Table 6, competitive across broad benchmarks, MMLU, Simple QA, IFEVL Sysbench, Multi-Challenge. Notably on Simple QA, factual knowledge, performs similarly to models with nearly double its parameters. DeepSeek v3 R1 highlights parameter efficiency, surpassed GPT 4.1, DeepSeek v3, Kimi K2 on Sysbench, outperformed GPT 4.1, DeepSeek R1 on Multi-Challenge, robust general capabilities. Finally, safety, Table 7, using Safety Bench, strong overall score of 89.87%, highly competitive with Kimi K2 90.48%, GPT 4.1 89.71%, robust in ethics and morality, mental health, physical health. Acknowledges room for improvement in unfairness and bias, shows well-rounded model prioritizing responsible AI.
Beyond automated benchmarks, the paper highlights hands-on experience through human evaluations. This often reveals real-world usability, coherence, nuanced understanding, especially for open-ended problems. What did these reveal?
Human evaluation provided crucial qualitative assessment, essential where coherence, relevance, creativity matter. For general chat, Tables 8, 9, 10, across English, Chinese, other languages, GLM-4.5 consistently achieved highest average scores against DeepSeek R1 0528 and Kimi K2. A single evaluator scored randomized responses 0-10, minimizing bias. Excelled in math, objective QA, text gen, and English. In Chinese, standout in text gen, logical reasoning, code instructions. Maintained lead in other languages too, truly multilingual, broadly capable chat model. For the coding agent, figures 12-13, used CC Bench, interactive benchmark with 52 programming tasks and isolated containers, human expert testing. Tests understanding, planning, execution, debugging. In head-to-head evils, strong against open source, competitive against closed source, 40.4% win rate for Claude Sonnet 4, 53.9% is Kimi K2, 80.8% is Qwen 3 Coder. High success rate for developers, also highest tool calling success rate, 90.6%. Efficient token usage. Highlights agentic execution robustness. This raises the question, how does it handle nuanced translation? Internet slang, cultural context, difficult for traditional models. Specific translation evaluation, Table 12, on 100 challenging cases. In blind human evil, GLM 4.5 significantly outperforms specialized models. QuantumT plus Turbo, SeedX, average score 1.71 versus 0.38 to 0.65 range. Impressive examples, accurately translated yards, internet slang, calico cat, not princess. Understood domain nicknames like FB for Canon lens. Shows superior contextual understanding, unified knowledge beyond literal translation. Lastly, for logical reasoning, Table 11, to mitigate data contamination, they built a new challenging set of novel logical problems. Human experts scored responses. GLM 4.5 performed on par with leading models like Gemini 2.5 Pro, DeepSeek 0528 scores 62.0. Indicates robust ability to tackle unseen complex logical challenges, genuine reasoning, not just memorization.
So what does this all mean for the broader field? The GLM 4.5 series, with its thoughtful MOE architecture, multi-stage training, sophisticated post-training RL, truly stands out in unifying agentic, reasoning, and coding capabilities. The depth of detail in the paper, from data curation to hyperparameters to extensive evaluation, provides a compelling argument for its position as a leading open-source foundation model.
Right. If we connect this to the bigger picture, GLM 4.5 clearly demonstrates that parameter efficiency, combined with deep understanding of training dynamics and multifaceted RL, can yield models that compete with and often surpass larger proprietary counterparts on critical real-world tasks. Key takeaways: strategic depth over width for reasoning, innovative data synthesis for agentic tasks, tailored RL approaches for distinct domains, actionable insights. The open release of models and evaluation toolkit is a significant contribution, democratizing access, advancing research and reasoning in agentic AI.
Absolutely. This deep dive into GLM 4.5 truly highlights the innovative paths researchers are taking to push LLM capabilities forward. Proving careful design, meticulous training, sophisticated post-training lead to remarkably efficient, high-performant models. For you, the listener, this offers clear insight into the cutting edge of generalist AI models and the complex, elegant engineering behind their unified abilities. Until next time, keep exploring, keep learning, and keep asking those deep questions.